Hello students, welcome back. In the previous video, I got a little bit carried away and spent a bit too much time in 3D examples and 3D visualizations. And consequently, I wasn't able to finish section 1. Sorry about that. Let's complete it now. This is the only one I didn't discuss. A map from a vector space to Rn is linear if and only if each component is a linear function. And the proof is left to the students. Basically, if each component function fi is linear, then the original function f is linear and vice versa. Here's an example. Okay, this is the example I prepared. And let's see, is this a linear function? Yes, indeed. If you look at the first component, what do we have? We have first order of everything, no second power, third power, or anything, and no constant either. Everything is just first power. Again, everything is just first power. Everything is just first power. So yes, each component is linear. And this is equivalent to this matrix multiplication. And as you have seen before, matrix multiplication, matrix times a column vector, defines a linear map. And here's a good example as a matter of fact. Let me just embed this one into the previous example or previous proposition. Just give me a moment. Okay, there you go. All right. Okay, let's go to the next section. The matrix associated to a linear map. Let's begin with some preparation. Coordinate vectors. Let V be a vector space with bases v1, v2, all the way to vn. And in that case, a row vector x1, x2, or xn, or column vector x1, x2, xn are called coordinate vectors if v is given by, well, this kind of expression, x1, v1 plus x2, v2 plus all the way up to xn, vn. You see, this is basis, so every vector can be written as a linear combination of these, and the linear combination is unique. And you can express it as either this form in column vector form or this form in row vector form. Either way, you're going to get the same thing. It's just a matrix multiplication, isn't it? So if you use this viewpoint, then you're looking at column vector. And if you take this viewpoint, you're looking at the row vector. Either way, it's the same thing. And those are called coordinate. And for basis, the coordinate vectors are unique. Most of the time, by the way, we'll use column vector. Okay, all right. That was just a bit of a reminder from the previous week. All right, let's begin. Let V and W be vector spaces with faces v1, v2 all the way to vn, and w1, w2 all the way to wm. Okay, n dimension to m dimension. And let V to W be a linear map. Then there is a unique matrix, unique m by n matrix, A such that W equal to LV corresponds to y equal to ax, where x and y are the coordinates of v and w respectively. So you see, you have a linear map L, then you can associate a matrix multiplication, and that selection is unique as long as you have the basis. Now, if you just have generators, not the basis, then the coordinate expressions are not unique, and consequently, the matrix expression is not unique either. But if you have basis, yes. Moreover, how do you find this matrix A? Please remember this formula here. We can find matrix A by taking each v1, v2, v3, these basis vectors, okay, and then take the linear map of those and get their coordinate expression with respect to these W's and write them as columns, and that happens to be the matrix expression. Oh boy, it's a little bit difficult to understand at this moment because it's highly theoretical and expressions are hard to understand. So before going over the proof, let's go over to examples first. Okay, here's an example. Let's see. R2 to R3, where standard basis vector E1 is going to 1, 1, 2, and E2 is going to negative 1, 3, 4. And find L of xy and express it as a matrix expression. We're going to get this. This 1, 1, 2 came from E1, right? First one. And write those as a column vector. And this negative 1, 3, 4 came from E2. So that's going to be a second column vector. So we need this. Matrix. And then we want 3 by 2. And this is 1, 1, 2. And negative 1, 3, oops. This is a matrix associated to this linear map. You see, in this expression, it was really hard to see. Now with this example, it's a little bit making sense. You see, first basis is going to 1, 1, 2. That goes to column. Second basis is going to negative 3, 4. That's going to the column. So that's your matrix A. And then L of xy L of xy can be written as A times xy or equivalently, this matrix times xy. So we completely identified that matrix. That linear map. L of xy is obtained by this matrix multiplication. So if we want to find out, say for example, L of 2, 3, okay, all right, 2, 3, as good as any. 2, 3, if I want this, then all I have to do is to calculate that matrix computation, 2, 3. And let's do this matrix computation. 2, so we're gonna get, let's see, copy and paste this thing. And I don't want second column. And let's go back to black. Okay, 2 times 1, negative 3 times negative 1, so 2 minus 3. And then 2 times 1, 3 times 3, so 2 plus 9. And 2 times 2, 3 times 4, so 4 plus 12, is that it? So what do we get? We get negative 1, 11, 16. For example, we can find any image like this. If I want L of negative 1, 6, what do? Negative 1, 6, and do your matrix computation, you're going to get different answer, and so on and so forth. So those are just trivial matrix computation, tedious but elementary. So that's not really the key issue there. The key issue is this one. How do we get this matrix expression? Find out those images of basis. E1 is going to 1, 1, 2. Okay, that's my first column. E2 is going to negative 1, 3, 4. That's the second column. And here's the matrix expression. By the way, if you open up, then you're going to get the solution. You see, 1, 0, that E1 is going to 1, 1, 2, and E2 is going to negative 1, 3, 4, and those are columns. Make sense? That's how you determine the matrix associated to a given linear map. Next example. E1 is going to cosine of theta, sine of theta. E2 is going to negative sine of theta, cosine of theta. Find out this linear map. Identify this linear map in matrix expression. Okay, let's go ahead and do that. X comma y. Let's see. Okay, x, y is equal to, let's see, we want 2 by 2 matrix now. Okay, 2 by 2 matrix. And E1 is going to cosine comma sine. So we want cosine, sine. And let's do color coding as before. Making sense? E1 is going to cosine of theta, sine of theta. That goes to the column. Next, E2 is going to negative sine of theta, comma cosine of theta. And let's emphasize those in red. And that's the matrix expression. And then we have to multiply x comma y. And that's it. As a matter of fact, you can stop here. Yeah, that's enough. But if you want to see the computation, then you can go ahead and do your matrix computation. So x times cosine, y times negative sine, so x times minus y times sine of theta, and then multiply. So we have x times sine of theta plus y times cosine of theta. And there goes the matrix expression of this linear map. What kind of map is this, by the way? It's a rotation. Yeah, same thing we just did. Column, column, so column, column. And then here's a visualization as a matter of fact. Okay. Yep. X cosine of theta, y sine of theta, minus y sine of theta, x sine of theta, y cosine of theta. It's a rotation. Okay, that picture looks a little bit better. And we used to do these kind of things. Let's run it again. Okay, that looks a little bit better. So if you have rotation by alpha first and then rotation by beta later versus rotation by alpha plus beta directly, and each time you are doing this linear map, and if you do, let's see, first computation, that'll give you up to here, blue, and then another computation that'll give you up to red. So from here, 1 comma 0 to x comma y, or cosine of theta, cosine of alpha comma sine of alpha, and then another rotation by beta, you get something complicated like this again, because, just follow the definition like this. And then go back and start from 1 comma 0 and apply the angle by alpha plus beta directly. Then you get this green. And if you compare the end result, this one and that one, the second line from here and then the second line from there, these two have to be the same, as you can see in this picture. You see, you end up with the same place. And if you compare these two, the second line and the second line, what do you get? Cosine of alpha plus beta is this, and sine of alpha plus beta is that. And that's how we used to prove the sum and difference identities of sine and cosine. Do you recall this from trigonometric class? Well, I do go over that in trig class, but I leave this as an optional topic when I teach trig, so many people must have seen this for the first time. But with matrix computation, we can actually handle this. Let's see, do we have another example here? R2 to R2. Oh, okay, all right. This is a little bit different. Previously, E1 is going to something, E1 is going to something, E2 is going to something, E2 is going to something. So we have this column expression directly, but this time a little bit different. This is not E1, 1 comma negative 2, and this is 4 comma 1. So how do you handle that? Well, let's assume these matrix expressions exist and then set up a system of linear equation like this. There gotta be matrix associated with this linear map, you see. E1 is going to A comma C, and E2 is going to B comma D. Maybe I should specify that. F is sending E1 to AC. And F is sending E2 to BD. And if we knew AC, the image of E1, and BD, image of B2, then it's kind of like the previous problems. But this one is a little bit harder. We don't know those. But you can set up matrix expression like this. You see? This is E1. So image of E1 goes there. And this is E2. And image of E2. So that's a matrix expression. And then 1 comma negative 2 is going to 0 comma 3. Okay, let's set up. This matrix computation, ABCD times 1 comma negative 2 is equal to 0 comma 3. That'll give you an equation. A system of equations. System of linear equations, actually. Everything is linear here. If you do matrix multiplication, what do you have? 1 times A minus 2 times B, indeed that, is equal to 0. And then 1 times C minus 2 times D, that's equal to 3. We get we get one system of equation. And then we have more. We have the second condition. 4 comma 1 is going to negative 1 comma 3. So this matrix times 4 comma 1 is equal to negative 1 comma 3. So what do we have? We have 2 equations and 2 more equations. Come on, 2 equations here, and then 2 more equations there. So we have 4 equations and 4 unknowns. Yes, we can solve it. The solution is going to be tedious. And, oh, I decided to do this computation. Okay, all right. It may be time consuming if you actually sit down and try to do that. But let's go ahead and do this. So set up the first and second line. So what do you get? A minus 2b equals to 0. So I guess I'm using substitution method here. A is equal to 2b and then c equals to 2d plus 3. And then I'm going to plug those into the next equations here. Yeah. And then how to solve those? Either elimination or substitution. You're going to get something like this. A is negative 2/9, B is negative 1/9, C is 1, D is negative 1. Okay, so now that we have A, B, C, and D, we can go back to the matrix expression and then put those back. And finally, we identified the linear map like this.